Hello, class. Sorry that don't feel like driving to school under snow only for one class. So that's why I decided to do this at home. Unfortunately, I left my school computer in my office because I thought I would go in. So I'm using my home computer, and I don't have PowerPoint. I don't have the Microsoft Office on my MacBook, and that's why I didn't download it. When I download it, and it would look weird. So I'm just going to use it like what you see here. And if there's something I need to write on the whiteboard to explain better, we can do that when we go back to face-to-face. Okay, like you can ask me a question if you don't understand what I say through this, but I will also get out the pen later on. So today, chapter 4, we are talking about probability. And also I created a Dropbox for you to drop off your text 1. If you don't have to put it on to the Dropbox, you can always bring it to class when we have face-to-face class. So because this is for some students, this is self-paced. So for you guys, it could be self-paced too. My dog is barking. Just a second. Sorry. Oh my God. Okay. So chapter 4, we will talk about probability. Okay. And so we'll talk about probability and then some rules for more than one event. And then what are the counting principles. So the introduction to probability. Probability shows us a chance, possibility, whatever, something will happen. And usually probability is happening between 0 to 1. Okay, it's a value range from 0 to 1. When it's no chance this will happen, the probability is 0. So let's say the probability of school closed tomorrow, Wednesday, is 0. Yeah, I shouldn't say that, but it's almost unlikely we will have snow again tomorrow. And then if the event is absolutely going to occur, then probability of this happen is 1. So tomorrow we will going to have a class, not for this class, but school will be open tomorrow. So the probability will be 1. Okay, so, and then there are some different definitions. The experiment is the process we use to measure or observe some activities to collect the data. Okay, so when we throw the dice, that's like several times, that's our experiment. And then the sample space is the possible outcomes or the result. Like when we throw the dice, we will always have 1, 2, 3, 4, 5, 6. So that's the sample space. Okay, so the next, and then the event is the outcome of one experiment. So the outcome or outcomes is a subset of the sample space. So the event will be when we conduct the experiment, that's the outcome of the event. The simple event is we only do it once, like we throw one dice once. Okay, so the example of simple event is throw the dice with a 5. Yeah, so that's one outcome with one event. So some other examples of the sample space are when we flip a coin, then we have heads and tails. So we have 2 outcomes. And then the multiple choice question, if there's 5 answers, then it's A, B, C, D. If it's 4 answers, it's A, B, C, D. And then when we inspect a product, it's defective or not defective. When we pick a card from a standard deck, it's 52 cards in one deck, right? So yeah. But if we pick a card with spade, okay, the color, not color, how do you call it? The symbol is spade, then it's 1/4, right? So there will be the spade we have 13 spade. So different method to assign the probability. So we have classical, empirical, and subjective. So first we will talk about the classical. So the classical method is used when the number of probability outcome of event is known. So like when we throw a dice, there are 6 different numbers. If the dice is fair, then we know there's 1/6 of chance to get each number, right? So usually when the number of possible outcome of the event is known, then the possibility will be the number of possible outcome divided by the number of possible outcome that constitute event A. So if we say when we throw a dice, the number is 1, then the possibility is 1/6 because there are totally 6 possible outcome. Okay, so that's that. And then, so here's the similar example, but the roll of 5, then it's 1/6 of chance to get number 5 when we roll 1 dice. So that's the classical examples. So in theory, if the dice is fair, we have the same outcome for for each number occur. So, for each number show up, it's like 1/6 of chance. So the second one is empirical. So empirical is we will conduct an experiment to observe the frequency of certain thing happen. Okay, so it could be like a lot of time business, we do this to like collect data, like this, let's say this class, I have 30 students, and then the empirical data will be, I collect data from you guys, say, oh, do you like the class or do you hate the professor? Okay, so the number that says yes, maybe let me say 2 people hate me in this class out of 30. So the possibility of, in my class that people hate me is 2 out of 30. Okay, so that's what 1/15, almost 6%, around 6%, 6.6%. So that's a possibility. So the frequency of some event happened over the total observation. Okay, so that's the empirical. So one example is they survey 400 new graduates and then ask them how much they owe in the student loan. So these are the results. Okay, so have 30,000 and more, 47 students, 20 to 29, 29 and 999, 66, 10,000 to 20, not over 20 is 144, 5 to 999, 9,999 is 102, less than 5,000 is 41. So when we ask the possibility of the graduate that all student loans is between 5,000 to 9,999, 9,999 is 102 divided by 4. Let me get a pen here. Okay, so it'll be here, right? 102 divided by 400. Okay, how about the possibility that a graduate has 20,000 and more in student loan? So then we can look at 20,000 and more. Let's here, this is 20,000 and more. So we have to add both up. So in this case, it's 113. Oops, change another pen. So it should be 113 divided by 400. Okay, so that's B. Okay, so that's the whatever it happened. Okay, the frequency in for certain event over the total observation. Okay, so that's this. So this is the answer, like what I didn't calculate it, but so this is when when you write the test or when you write this is the standard way to write it. So we know this is a possibility that the student loan is between 5,000 to 9,999. And then this is possibility of student loan greater than $20,000. Okay, so these are the possibility. And then law of large numbers means that when we collect the data large enough, okay, when we do the experiment large enough, usually it would be very close to the classical probability, like when we flip a coin. So maybe when I flip coins for 5 times, then I might get 5 heads or 5 tails, okay? But if I flip it for 100 times, then the number of heads and tails will be very close to 50%, okay? So this is the law of large numbers. And then the last method of assigning probability is subjective. So subjective is we use our experience or the intuition, okay? So like, oh, so now when you ask me, what's the probability that inflation will be greater than 4% next month, okay? I won't say 4%. I think the possibility the inflation will be greater than 5% next month. Well, I would think it's like 100%, but this is it's not a good estimate, but based on the intuition, you know, people say, oh, the possibility of the inflation will be greater than 4% next year, maybe 30%, you know, 40%. So it just depends on the intuition. In this case, because we know the inflation is kind of high now, so like this one, in this case, I would say 90%. Okay, so that's that. And then we have some basic rules for the probability. So if PA equal to 1, that means the P possibility of A happened is 100%, is 1. But if PA equal to 0, that means the possibility of A happened is 0. Okay, so this will not happen. And then the possibility have to range between 0 to 1. Okay, so that's another rule. And then the last rules is the sum of all probability for the simple event in the whole space must be equal to 1. So one good example is when we throw the dice. Okay, let me change my pen. When we throw the dice, 1, 2, 3, 4, 5, 6. So we know there's 1/6 of chance to get 1. Okay, and then 1/6 chance to get 2. And then 1/6 chance to get 3. And then 1/6 chance to get 4. Sorry, it takes so long. And then 1/6 chance to get 5. And then 1/6 chance to get 6. So when we add up everything here, it should be equal to 1. Okay, all the sample space, when we add up all the event in the sample space, okay, which is 1, 2, 3, 4, 5, 6. In this case, it should be equal to 1. Okay, so that's that. So next page of the rule 5 is the complement of event A defined as all of the outcome in the sample space that are not part of event A. So that means if let's say throw a dice 1, the dice number is 1, it's 1/6, right? So the complement means that, oh, if the possibility that we don't throw 1, which is 2, 3, 4, 5, 6, will be 1 minus 1/6, which will be 5/6. Okay. So in this case, A is 1, get a dice. You know, when we throw a dice, get number 1. And PA, how do you call that, apostrophe, is 2, 3, 4, 5, 6. Okay, so not A. PA plus P not A is, when we add it up, it should be equal to 1. Okay, so that's the 5th rule, the complement. rule. So we have a contingency table we can use to show the number of event happened, and then it's classified according to two category variables. So when we have a contingency table, so for example, we have one is S or not S for the car, for the deck of 52 car. Okay, so this is one category, and then the other one is the color is red or black. Okay, so we have this is the contingency table. So we have 4 cars as S, but out of the 4, 2 are red, 2 are black, and then we have 24 non-S cards, 24 red, 24 non-S cards black, but totally we have red cards, 26 red cards, 26 black cards. Okay, so there's the contingency table, and then totally we have 52 cards here. So when we look at the contingency table, the possibility to get an S is 4, right? Because, I mean, not 4 over 52. So it's 1 over 13. Okay, so that's 7.7%, 4 over 52. The possibility to get red cards is half, right? Because half red, half black, 26 divided by 52. So what if I say the possibility to get a red S, then it's 2 over 52. Oops. So here will be 2. So here will be like 385, 0.385. Okay, close to that, or 386. So that's the contingency table. And then we have the intersection of event A and B. So there might be some overlap here. Okay, so that's the P, A, and B both happened. Okay, so this is P, A, and B. So the rule for that is, so like that's the possibility of 2 events that's join possibility. So that means when the card is S and red, the possibility is 0.3038. Okay, so that's, we denote it as P, S, and this is and red. Okay, so this is the A and B. Okay, and then this one is A or B. Okay, so A or B is denoted as this. I don't know if you can see that. It should be here. This is or. So this is and this is or. So it's different. A and B, S or red is this one, but either S or red, then it will include all the red, and then it will include the black S. Okay, so no, I don't know if I say it right. A's. It should be A's, not S, right? It should be A's. Yeah, so it should be A's or red, not S. So A's or red. So it's 2 plus 2 plus 24. 4 plus 24. That's 28 over 52. So that's 0.538. And it's denoted as this P, A's or red. Okay. And then the addition rules is, if the possibility is the 2 events are mutually exclusive, like this, okay, like this, like the chart, there's no overlap, that means they are mutually exclusive. So the possibility for A and B happen will be, you not A and B happen, it will be 0. But for A or B, you basically add up these 2 events. But when it's not mutually exclusive, they'll have some overlap. Okay, so it's a little bit different. So when there's mutually exclusive, the A or B event, it will be A plus B because it's either A or B. But if it's not mutually exclusive, okay, when A or B happened, it will be A plus B minus the overlap because we are calculating this area, right? If we add this, oh my God. Okay, so if I let me do this. Okay, so if I calculate, like add A here, you can even draw. It include the middle part, right? The overlap. Okay, but if I want to calculate, I mean A and B, then it should be A plus B, right? And then this area, we actually calculated twice, we added twice this area, so we have to minus PA and B. So that's the calculation for the not mutually exclusive situation. So the addition rules, like here, like the one we use, the possibility for A or rate, A's or rate is the possibility of A's plus possibility of rate minus the possibility of A and rate. Okay, so that's calculating like this. If we have something simple like this table, what we can do is just pick the event, like 24 plus 2 plus 2. That's how we calculate it. Yeah, so we don't have to count. We don't have to count this area twice. That's how it's all it says if it's not mutually exclusive. So this is that. Okay, A or B is this one plus this one minus this. So how about try to do this one? Okay, I would review this next time, but you guys should try to do it. So what's the possibility to see customer purchase warranty? So this is to purchase warranty, right? So we have total 11 customer purchase warranty divided by total. What's the possibility? 40 or older and choose not to purchase. So 40 and older and then no warranty here divided by this. Okay, so the possibility at less than 40 or choose to purchase. So less than 40 is here. Okay, and then no choose to purchase is here. So it's this. So it's actually these three, right? Yeah, divided by 60. So that's it. Oh, there's the answer here. Is it? No.
Sorry, I don't know that one.
See, my Alexa is kind of stupid. Anyway, so the conditional probability that given A happen in the condition that B has occurred. Okay, so example is, so if given that event B has occurred, which is completed the prep class. For those who complete the prep class, they score 601 to 800 for their math SAT. Okay, so the possibility for that will be what? Okay, so what we do is we can use PAB divided by P. Oh my God, Milo. So we can use this PAB, PA, and then this B is PA and B divided by PB. So whatever like under here will be under. Or PBA is this way. Okay, so PAB here is 0.314. Okay, because we just use this divided by this. But if we want to calculate it, we can use PA and B, which is PA and B here, 22. And then 22 divided by this. Here. So P and AB 22 divided by 250 is 0.088. And then PB is 70 divided by 250, 0.286. And then do this divided by this. It's the same as given the fact this happened. Okay. So that's the same thing. But if we have the raw data, we could just use this. It's like more intuitive. Yeah. But if we don't, we only have like PA, PB, and then PAB, then we know we can use the data we have. Like we can use PA and B divided by PB, PA and B divided by PA to calculate those conditional data if we don't have this raw data. But if we do have raw data, it's easier to just calculate 22 divided by 70. Yeah. Okay, so independent and dependent. So two events considered independent of one another if this doesn't have impact on the other one. So for example, let me think. Try to think something that impact. Oh, let's see. A tornado happened in Oklahoma. Will not have an impact on whether or not we have snow day tomorrow, right? So that's independent. And if the occurrence of event affect the occurrence of another event, then they are dependent. They will affect the the occurrence. So like if the inflation rate is high, then our interest rate will be higher. Okay, so that's dependent. So based on this, to determine whether or not A and B are independent is if given the condition B happened, A happened, it's the same as A happened. Okay, that means they are independent because no matter B happened or not, A's possibility is the same. Okay, but if P A B is not equal to PA, then they are not independent because given the fact that B happened, the possibility of A happen is not equal to just the possibility of A. That means they are somewhat, affecting. B is somewhat affecting A. They are somewhat affecting each other. So one example here is if you're interested in math or let's say statistics, okay, and you get 70%, 80% or better in your grade is 72. So if you're interested, your chance to if you are interested in math, the possibility to get 80% or higher is 63%. But for those who get 80% or higher, the possibility is 55%. So that means if you are interested in statistics, okay, event is you are interested, the possibility to get 80% or higher will be higher than if you're not, like then just to get 80%. So that means actually being interested in the subject may be not help, but it's related to higher possibility to get better grade. Okay, so that's that. And then formula for multiplication for the dependent event is BAB is, like we say, PA and B, it's denoted as P, A and B, okay? So divided by PA or PB. So whatever on this side, you can look at it like a fraction. So B is like underneath, okay? And then A is underneath. So it's like this. Okay, and then that means PA and B equal to PB times PAB, and PA and B equal to PA times PBA. Okay, so these are the multiplication calculation for that. So one example, if the rain is forecasted and then you carry umbrella. So the rain forecasted, the 30% chance rain. And whenever the rain forecasted, you will carry your umbrellas, percentage is 90%, okay, 9.9. So what's the chance that the rain is actually forecasted and you carry umbrella? So there will be 27% that rain happened and you will also carry the umbrella. Okay, so that's that. And for the two independent event that they don't affect each other, basically just PA and B is PA times PB. Okay, because this one, like we show you before, okay, when this is it's independent, PBA is equal to PB. So basically it's just PA times PB. Okay. Oh yeah, here. This one equal to PB. So let's look at the example. So the table of frequency to probability, blah blah blah. So this one is the math class, right? And wait, what is this? Okay, so the metal is gold. What is possibility that's won by US? So they are they independent? I think they are independent. The metal won by Russia, the possibility that's bronze. So so what do you think the US and gold, is it independent or dependent? Okay, so you know, so that's a calculation that we can kind of do later on. Like next time I'm going to go through this. So basically, what's the possibility that PA B is happened, okay? When it's gold, and the possibility that's owned by US is this, okay? And then the possibility on the gold and US, is it the same, or it's independent or dependent? Okay, so let's see if we can calculate that. And then we have the Bayes theorem. So to calculate PAB from the information of PBA, so we could just basically use the PAB. Okay, PAB is equal to PA times PBA divided by PB. Okay, so because basically PA times PBA is PA and B. So PA and B divided by PB is PAB. So that's it. So suppose event A has two mutually exclusive part A1 and A2, and then there's some conditional probability B over A1 and B over A2. So the possibility of A1 over B will be PA1 times PBA1 divided by these two possibility. Okay, so let's see if we have example. So when we can add up all the possibility here, okay, and then use the PA something times PB over A something. So they will give us the PAI. Okay, PAI and B. Yeah. So that's that. So one example here. The credit score and the PNC bank customers. So we have the customers that the credit score is less than 6%, percentage of they get the credit card credit score is, when they get less than 600, then the 25% of chance they would, let me see, I forgot. They would be late on their current payment, 25% of chance. When the credit score is between 600 to 700, 45% of chance they will be late on the payment. And then if it's over 700, 30% of chance they will be late, okay? So we want to, the event B is the customer is late on his or her credit card payment. So customer who with the credit score less than 600 are late with the payment 40% is PB over A1 is 40%. So the customer credit score between 600 and 700 and late is 10%. Where's 10%? I don't see that. That's weird. B, wait. Huh? 6.2. Okay, so this is another condition. Event B is okay. So, so these are the percentage of the credit score. And then they have another condition that's, that they are late for their payment, 40%, 10%, and 5%. Okay, so these are the condition. So to calculate using the Bayes theorem to determine possibility that the customer has credit score less than 600 and the person is late for their credit card payment will be PA1 over B. So we calculate all the possibility. PA1 is 25% of chance that's lower than 600. And then PBA is 40%. They will not pay in time. They'll be late. And then we add up all the other possibility. Okay, so we get 0.1 divided by this. It will be 0.625. So 62.5 chance that late payment will be from a credit score less than 600. So that's the Bayes theorem. Yeah. So this one, suppose Super D is a major video distributor that purchased blank DVD from two suppliers. Disc maker who provides 62% of DVDs and media supply provide remaining 38%. Historically, 3% of DVD Super D purchased from this maker is defective. 2% from media is defective. Given a random selected DVD found to be good, using Bayes' rule to determine possibility DVD coming from media supplier. So the possibility that has defective is 3% and 2%. So means the possibility that's good is 97% and 98%. Okay, so how do we calculate that? Oops. So that's something we will discuss in the future as well. But remember, we want to calculate the possibility that's good and it's from media supplier. So yeah, so we yeah. So so think about this, and then we will do. Let me just write it really quick. So the possibility is from media and good is 98% is good. Okay, so it'll be 0.98 times media is 38%, 0.38. Okay, divided by 0.98 times 0.38 plus, let me write it here, okay, plus the good one from the disc maker, which is 0.797 times 0.62. Okay, so that will be the possibility that's the good one coming from media. So that's that. So let's move on. Next one, counting principles. So the fundamental counting principles are if there are several choices for the first event, and then another options choices for the second one, and then the n choices for the n event, the total possibility is all the possibility that we multiply together. Okay, so one example is, well, so that means if there are 3 digital model number to be selected using the initial letter ABCD, followed by 2 numbers from 0 to 9, how many different numbers are possible? So we have select ABCD, 4 possibilities, okay, times 2 numbers, each have 10 options. So it's 4 times 10 times 10, 400 possibility there, okay. And then we have a permutation. Permutation is when, how do you call this? I forgot. And is it epsilon? Epsilon? Oh my goodness. So this is n epsilon. I'll look it up. And it'll be equal to n minus 1 minus n minus 2 times, blah, 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 till it's 1. Okay. So by definition, the 0 epsilon is 1. So permutation is usually this one, n epsilon, divided by n minus x epsilon. Okay. So this is the permutation. When we select permutation of certain number object, selected x at some time. So one example, if we select ABCD here, select 2 letters from 4 options. So it will be P4, 2. So it'll be 4 times 3 times 2 times 1 divided by 1 times 2. Okay. So that will be 12. And then the permutation is A, B, A, C, A, D, B, A, B, D, B, C, C, A, C, D, C, C, B, C, D, D, A, D, B, D, C. Okay. So when we have permutations, we can see that the orders, the sequence actually matters, because you see we do have DC and we have CD, and then we have DB, we have BD. So that's the permutation. Okay. And then we have the combinations. Combinations, we'll pick numbers, but whatever order we picked doesn't matter. Okay. So that would give us the C nx, that's n epsilon divided by n minus x, and then epsilon, and then nx. Okay. So the example here is to pick 4 letters from 2, it'll be 4 epsilon divided by 4 epsilon, and 4 minus 2, 2 and 2. Okay, so it will actually give us 6 combinations. Like the previous example, we have 12 because we have 2 same combinations but different orders. Okay, so permutation, and that's the difference between permutation and combinations. So I think that's it. So quick question. 7 letters A to G, found the permutation for following case. Letter A must be in the middle position. A, B, C, D, E, F, G. How many permutations are possible? So if well, let me just draw it. You guys can think about it. So we have 7 letters. Oh no, I shouldn't use that. We should use this. Good with writing. So 1, 2, 3, 4, 5, 6. Okay. So in the middle is this one. So A must be here, right? And then here we will have 6 combinations, right? So we have 6, and then this one we have 5, 4, 3, 2. So the different permutation is 6 times 5 times 4 times 3 times 2. That will be the answer for this permutation. Yeah. Can they, but they didn't say if we can repeat. Yeah, well, I think in this case we can repeat. So it'll be 30 times 4, 120 times 6, 720. Okay. So that's the first answer. And then the second answer will be A cannot be the first letter or the last letter. How many permutations are possible? So it's difficult. That means the first one has 6. They cannot be first. Okay, so I have 6 possibility. Second one, I have 7 because A, B, C, D, F, G. Third one, it has 5, and then 4. Oh, 8. Well, I don't know if we need to repeat the letter. So if we don't, then it's 6 times 7 times different things. But if we cannot be in the first letter or last letter, so it means the first one and last one, we have to take out the A's possibility. So think about how to calculate this, and then I'll show you guys. Try to so these are the, yeah. So we will talk about this later. Yeah. So these are different permutation. Okay. The answer, but I will discuss this next time. So try to think about this, and we should have the, I don't know why the answer didn't show up, but that's fine. So so try to think about this to see whether or not you know how to do this, and then we can kind of discuss next time, okay, in class. So I'll see you guys next time. Bye. How do I close it?